diagram of a stress versus strain curve, okay, is created, and what is the information can be obtained from this curve. Okay, right, just a second. All right, another properties that we can determine from the tensile strength behavior is tensile test is a Poisson ratio. Okay, what is Poisson ratio? Poisson ratios is the property of material that will tell us how much the material will deform in a different behavior. We call it lateral direction. Okay, when you elongate a sample specimen for the tensile test, okay, basically we measure the elongation of the specimen. However, there is another quantitative measurement that can be obtained, which is the reduction of the dimension at the measured gauge. Okay, for example, like this one. Okay, this is the longitudinal direction. What does it mean? It's a direction of the load given in the tensile test, or whatever the load direction. Okay, longitudinal direction is following the direction of the load. In this case, it is a tensile direction. Okay, so the reduction, okay, this is the original, the green color is the original dimension, and the orange color is the dimension of the specimen or whatever the structure during applied load. Okay, so the increase of the length can be seen here. Okay, okay, so you can see that the length of the structure is increased. However, the lateral direction, for example, this is X direction, is a direction following the direction of the load, and Z and Y is the cross-section direction. Okay, so the reduction in Y direction, the size direction, the reduction of size at Z direction is decreased. Okay, after the load is applied. Okay, you can see this is original length at Y direction. This is after you apply the load, so it reduced in length. Okay, so what is this? Okay, sorry, the error. Okay, so the strain at X direction, which is the direction of the load, is measured by the increase of the length divided by the original length at X direction. And Y-axis is negative Y because it is reduced. Okay, so the reduction divided by the original length at Y direction, and Z can be calculated like this. So basically, X, Y and Z strain value is similar, but the Y strain, okay, strain at Y direction is proportional to the X direction, and same goes to the Z direction. It is proportional to the strain at X direction. So the ratio between this strain at Y and Z direction is equal when you compare with the strain at X direction. And this ratio, okay, Y over X and Z over X, we call it material constant. So the Poisson ratio is actually the material constant for the changes in dimension at this direction. Okay, so lateral and longitudinal. Lateral, it can be Y or Z. Y negative because it is reduced in dimension. Okay, Poisson ratio is unique for homogeneous and isotropic materials only. Okay, So meaning that the behavior of material property is similar in any direction. Okay. Why negative sign of this value? Because longitudinal elongation causes lateral contraction, which is negative strain, and vice versa. Meaning that if you give a compressive load, okay, you will obtain that lateral direction is positive, but longitudinal elongation is negative. Okay, lateral strain is the same in all lateral radial direction. Okay, Poisson ratio is dimensional, and basically it is between 0 until 0.5 value. Okay, and actually if we construct the curve for stress strain curve, not only for tensile, but if you have a structure and we want to investigate the effect of the load to the structure, okay, to the elastic plastic behavior, and your structure experience torsion load, okay, we also can obtain the same result, similar to the tensile strength. Shear means that you twist the structure. What is the example of this kind of torsion load? Okay, for example, whatever let me think. Okay, you know, wire rope. Okay, the wire for the suspension to for the crane to lift up the load, or the suspension for the bridge. Okay, you hang the bridge using the wire rope. Okay, it is a steel and it's forming a rope by you combine several strands of the wire and become a rope. Okay, tali dia berpintal-pintal tu kan. So when you give a tensile load, each of the wire will experience torsion. Okay, torsion. So you need to know what is the limit for the torsion. Okay, you need to know whether the limits, the load that you give a certain torsion limit. Okay, whether it will turn into the plastic deformation behavior. So how they obtain this result? They also construct, okay, by giving the load at torsion direction. Okay, so the torsion versus the strain at the shear, like this one. Okay, the graph. Okay, this is torsion load, and you can see the deformation after the shear loads is subjected to the structure. Okay, the strain loads, the stress, shear stress versus the strain can be plotted, and the result is similar to the tensile stress versus the strain. Okay, at the longitudinal direction. So material will exhibit linear elastic behavior until it reaches the proportional limit. This is the limits for the elastic, and then you may see the plastic deformation behavior. And the method to measure the Hooke's law for the shear also similar. You measure the slope for the linear curve. Okay, this part until the limit, right? So what is it? This torsion load at this limit divided by the strain at this linear limit. Okay. So G is the Young modulus, elastic linear behavior Hooke's law for the shear stress versus strain curve. So the ultimate shear stress can be determined similar with the tensile stress, which is the maximum load of the torsion, and then the failure is similar. So another properties that we measure to determine the material properties of the material is the hardness test. Okay, in many applications, components should have not only a high strength but also a high wear resistance. Okay, why? Because we want to ensure that there's no changes in dimension due to uh, um, the interaction between the surface of your component with the surrounding. Okay, for example, if you have very soft surface of your for example, the turbine blades. Okay, the turbine blades. There are so many particles, exposed to many particles. For example, for the jet engine, if the surface is very soft, meaning it will deform due to the interaction with the particle from the air of very high velocity of the air that impact on the surface of your blade for the jet engine. It will create notch or crack, starting point for the crack. Okay, so we want to ensure that the structure must have a certain behavior in terms of the hardness. Okay, which is can be influenced the wear resistance. So when it's subjected to any interaction or friction with any situation, so it won't create any cracks. Okay, this generally applies whether two or more components are in moving contact with each other. Okay, this is especially for the real structure that no matter how it experience a friction. For example, the gear, okay, it touch from one to another. The shaft, okay, the bolt, okay, is contact with the surface of another part, the pin itself. So hardness is very important for this kind of component. So hardness test is a measure of a material's resistance to localized plastic deformation. For example, a small dent or a scratch. So if you want to ensure that your structure have high hardness, so this material should ability to resist this kind of deformation. The deformation is not a very huge load, maybe a very small load, but very localized. Okay, scratches, right? Maybe it's not very high load, but it's just a small dent and scratches. Low load also can create this kind of deformation. However, okay, this determines the hardness of the materials. All right, one method we can use Rockwell hardness test. In this test, hardness number is determined by the difference in depth of penetration resulting from the application of an initial minor load followed by a larger major load. Okay, initial load, the penetration is measured at the first minor load, and then it increase the load, major load, and decrease the load, and let the initial load maintain in the testing. So we will see how much the load, the larger the load, how much the deformation of this or indented surface of your material. Okay, the larger the indented area means what? If you obtain the larger indented area, so what does it mean? Area can penetrate more. It means it is not hard, it is soft, it is ductile. Okay, so if the penetration is small, means it is very hard, it resists to the penetration. Okay, so this test is done for Brenner's test. This test is done by forcing a hardness steel ball of non-diameter under a non-load into a surface and measuring the diameter of the indentation with a microscope. Okay. Oh, sorry. This one. Okay. A certain limits that need to reach for the second load. So the larger the loads means the harder the materials. The lower the F1 loads means it is a what we call it. It is soft materials. But for the Brenner hardness test, we look at the shape of the penetration. Okay, the larger the area penetrated, by this the what we call it, the indenter, the softer the materials. Okay, we measure the area, the deformed area, okay, with microscope and determine the value, how large, okay, the indented area. Vickers, okay, Vickers, unlike Brinell, Vickers use diamond shape, and we calculate the diamond shape to determine the properties, which is the hardness of the materials. In this test, using an optical method, okay, the size of the indentation diagonally left by the indenter will be measured. Okay, the larger the value of D1 and D2 means the ductile of material. Okay, the larger the indenter left by the indenter at the defined test spots in the specimen, the softer the material. Okay. So allowable stress is a measure of when you design, you need to know what is the maximum of the load. Okay. Basically, we take the value of stress. Okay. When basically what kind of stress that you need to look at. If you have one material, you know this is the list of properties of your material. For example, the tensile strength equal to 250 megapascal. The yield strength is 200 megapascal. The yarn modulus is 190 gigapascal. You have all the data sheet for the materials. But now you want to design what is the maximum load is allowed to be subjected, okay, on your structure. So what kind of the maximum load, okay, can be used to ensure it is safe. Okay, which element that you need to look at? Let's say you want to design the load is the in tensile load. So what is the properties that you need to look at? Anyone?
The ultimate tensile stress?
Ultimate tensile test. Okay.
Stress.
All right. Ultimate tensile test. All right. Okay. Let me show you. Okay. This is stress strength curve. Okay. Ultimate tensile test is here, right? Maximum load. Okay. This is stress. Okay. This is ultimate tensile test. Tensile stress. Okay. So okay, let's say you put this limit. So meaning that if I set the allowable, what is the allowable stress? Is it higher or lower than this ultimate tensile test strength? Lower. So how low is low? At the yield point. Okay. So meaning that you can use the load at here. Let's say this is yield point. Okay. This is yield point. Okay. Let's say sama lah ni. So means this is your load. You can use this load, this stress. Is that what you mean? Okay. Maximum like this. So meaning that beyond this, what happened?
Plastic deformation.
Yes, it will go to the plastic. This is the load that will give plastic deformation. Okay. So we basically, to avoid plastic deformation, we will use a maximum stress at the elastic limit. Okay, elastic limit, which is indicate the maximum point for the linear line. Okay, so this is linear line, maximum here, which is lower than yield strength. Okay, during the yield strength, what happened is the atom is starting to break the bonding, the slip will start to occur. Okay, the slip of your plane, atomic plane will start to occur. So basically, this is maximum load where it can give a deformation elastically. Okay. So is this the allowable the limits for your load for the stress on the structure? This one, is that allowable? Yes, actually it is not always yes, because why? Okay, so when we design safe, it is safe when it is lower than this. Okay, this is maximum. So let's say you want to you have a structure, okay, you design a structure perfectly, okay, where it can support load at this limit, for example 200 megapascal. Okay, 200 megapascal, right? So this is maximum load. And for example, you design a bridge, okay, it support a load at tensile or support load at the bending, okay, maximum is 200. And what happened if the bridge untuk highway, for the highway, what happened during the accident? There is some impact load, okay, during the impact load the stress will suddenly increase, so it will increase beyond this limit, so accident may occur. Okay, the bridge will deform plastically. So this meaning what? This is not the allowable stress. We need to give a safe level. So we use this one, yes, correct. We use these limits to choose the allowable load, okay, which is less than this load. Okay, one method we use what? The factor of safety. Okay, how to measure? Okay, this, what is the limit for the fail? Okay, it can, usually we use this yield strength lah, yield strength. Okay, yield strength divided by the allowable loads. Okay, this one, let's say we decide based on this one. Okay, safety. Let's say we want to give a double protection, meaning that half of the load before fail. Okay, so meaning that let's say this is 200. Okay, we want to make it half of it. Okay, so divided by 100. Okay, so 100, so it is equal to 2. The factor of safety is 2. Okay, maybe 1.5, but basically it is larger than 1. Okay, right. If load apply is linearly related to the stress developed within the member, then it can be expressed as the stress divided by the allowable stress. Okay, factor of safety must be larger than 1 to avoid potential of failure and dimension loss. It doesn't have dimension. Okay, specific value will depend on the type of materials used and it is its intended purpose. For example, you must know during designing something, you must identify which is the most critical failure that may occur. Okay. So in summary, engineering stress is defined as the instantaneous load divided by the original specimen cross-sectional area. Engineering strain is expressed as the change in length and divided by the original length. And stress strain curve is an important diagram to obtain mechanical properties of materials. Okay. Another elastic parameter, we call it Poisson ratio, represent the negative ratio of transverse and longitudinal strain. Hardness is a measure of a material resistant to localized plastic deformation. Okay, moving on to the next. To the next lesson. Okay, so this is the second part of this chapter, which is about a failure. Okay, this is very important. When you design something, you need to consider, always consider the failure behavior of the materials. Okay, this is very important. Okay, especially in any engineering application. Okay, so in this lesson, you need to be able to describe the mechanism of crack propagation for both ductile and brittle modes of fracture. You should be able to explain the phenomenon of ductile to brittle failure and define the fatigues and quick failure and specify the condition under which they occur. Okay, look at this. Okay, really stalwart. Tadi nak sebut lah. Okay. Okay. Ni nama author dia lah. Author pula. Orang yang ambil gambar ni Titanic pun ni. Titanic. Alright. This picture sketched by this author. Alright. Titanic fails. Okay. Why? Imagine this is very the first largest ship being designed. So what do you think? Okay, they are the first that design very thick metal steel for the body, for the ship hull. Very thick. They are very confident, very sure that it can be strong enough to crash the iceberg. They are very confident. Okay. However, when this ship hit the iceberg, what happened? Okay, it's broken, fractured into two pieces. Okay, why? They forgot something. They are not focused. They were unable to discover one properties. What is it? Okay, it is a brittle ductile transition. So materials, when they test in normal condition, they say, oh, this structure is a tough enough. Okay, have a certain toughness behavior. Okay, it can be strong enough to hit to crash the iceberg. Okay, but actually the metal change their behavior when the environment change. Okay, for example, like this metal steel. Okay, when the temperature is lower than 0 degree, okay, minus degree, it is not as tough as at the room temperature. Okay, it becomes brittle. Okay, remember, brittle material doesn't have sufficient toughness. Okay, brittle does not have sufficient toughness. Why? Because it doesn't have high enough ductility. Only ductile material can absorb the energy, the impact load. So that's the reason it becomes weak at a lower temperature. Okay, so what is this? This is the unexpected exploit buildings. The usual causes of material failure are incorrect material selection, incorrect processing, incorrect manufacturing procedure, inadequate design, or incorrect use. So fracture is the separation of a body into two or more pieces as a result of an imposed stress. Okay, remember, not just because we measure the dimension and what we call it, yield strength only, but the behavior of failure also is very important to design our engineering component. Okay, when we talk about fracture, okay, it involves two-step crack formation and propagation. Okay, in response to the stress. Okay, for metal, two fracture mode are possible. Okay, fracture mode. Bila materials tu patah, dia ada dua behavior yang berbeza. Satu dalam bentuk ductile, another one is in the brittle mode. Right? So when we look at the fracture behavior, we will understand the properties, the behavior of the materials. Okay, for example, like this one, ductile fracture. Okay, when we give a load, you can see the formation of void. You can see that a rough surface and the cone and cup structure. This is cone, cup structure. What else? The reduction in the necking. Okay, reduction in diameter of the specimen. Okay, imagine this is the specimen of the tensor test testing lah. All right. So the cavities that form due to the slip, okay, is a initial crack. It's a kind of crack. Okay, void tu adalah punca kepada crack propagation. So first initial necking, then small cavities. First necking, cavities, and then propagate. These cavities will propagate due to the load, and then fracture. Okay, this is behavior for ductile. Okay, if you observe the crack surface, this one, if you look at this structure at this point, okay, what you can see something like this. Okay, this is something like you can see spherical dimples. Okay, macam menggerutu. Okay. But for the brittle fracture, the fracture surface of a brittle failure is usually reasonably smooth, okay, and less or low plastic deformation. The crack propagates through the material by a process called cleavage, okay. So this is the crack formation. The atoms bond will detach due to the crack propagation. Okay, it can happen through the grain and also between the grain. Okay, depends on the it can be both. But unlike ductile behavior, usually it will occur between the grain. Okay, but this one inside the grain. Okay, transgranular. We call it transgranular. Okay, passing through all the grain. So meaning that it's cutting the grain. Okay, that's the reason you see a very smooth surface, bright under the visible light, what call it. By naked eye, you can see a very bright surface or smooth surface. Licin je permukaan dia. Dia tak menggerutu. Alright, unlike the ductile. Okay, by naked eye, you can see a very grayish surface. Kelabu-kelabu je, macam kelam je. But for the brittle, it is very bright, licin, sangat licin, berkilat, something like that. Okay, intergranular also can occur during the brittle fracture. So now you know ductile and brittle behavior. All right, brittle fracture basically for the high toughness, ductile and high toughness materials. All right, at low temperature, okay, compared to the normal temperature, some metal that would be ductile at room temperature become brittle. Okay, this is known as a ductile to brittle transition. Okay, remember this, ductile to brittle transition. This is what happened to the Titanic. Okay, because they don't study about this behavior, transition behavior. Okay. So this can be measured through the impact testing. Okay, we give an impact load and see what is the fracture behavior. Okay, this is our Chappie impact test.
All Pro-threaded products operates under the API Q1 quality management system and holds the licensing for critical fasteners under API 20E and 20F for bolting standard levels 1, 2, and 3. These and other certifications are made possible through the efforts of our highly trained quality staff using the very latest and sophisticated equipment. The Sharpie impact test, also known as the Sharpie V-notch test, is a standardized high strain rate test that measures the amount of energy absorbed by a material before it fails. The sample used is a rectangular specimen machined to 10 by 10 millimeters with a V-shaped notch. This is known as a Sharpie V-notch. It is cut into the specimen at a specific dimension to meet the relevant Sharpie testing requirements. The measurement needle is manually adjusted to 0 on the scale, ensuring that the energy absorption can be properly recorded at the point of impact. Depending on the type of material, the specimen can be tested at between an ambient atmosphere to minus 150 degrees Fahrenheit. The sample piece is an ASTM A320L7 stud, which requires a testing to be conducted at minus 150 degrees Fahrenheit. Once the required temperature is obtained, the specimen is held for a minimum period of 5 minutes. To begin the test, the Sharpie hammer is lifted into position and held in this position until the test specimens are cooled to the required impact temperature. Following this wait period, the Sharpie hammer is released, the impact is administered, and the impact absorption is measured. This process is repeated a total of 3 times on 3 identical specimens, and the average of all 3 measurements are reported for the set.
Okay, that's how impact test is being conducted. So it designed the specimen at a standard specimen size by following the standard, and they give the loads. It depends on the environment that you want to test, whether at room temperature, meaning there is no influence of temperature, or at very low temperature, because we want to see the brittle, ductile to brittle transition. Basically, brittle properties is obtained at a low temperature. Okay, look at this. This is a specimen, standard specimen size where you create a crack. Okay, this notch as a crack. Okay, initial crack. So where the stress concentration will focus at this crack. Okay, we don't want it to be cracked at this point or this point because we want it to be following standard. When you want to create a standard, you must do design a standard that can be followed for any materials. Okay, so for this one, when you create the notch here, so every sample, every material that you design will follow this standard, and it will fail at this point. So when we give a load directly at this position, the crack will occur here. So how much the material can absorb the energy indicates the toughness of the materials. Okay, so when we want to investigate the absorbed energy, the ductile to brittle transition, okay, we need to construct this graph, okay, which is absorbed energy by the impact test versus temperature. Okay, so ductile temperature, high temperature is room temperature. Okay, kenapa dia jadi macam ni? Macam ni lah, maksudnya kita start daripada lower temperature, kita buat next slightly higher temperature, slightly higher, maybe room temperature, maybe there are slightly higher than room temperature, 20 degrees, 30 degrees, 40 degrees, something like that. Okay, so metal biasanya tak ada perubahan lah daripada room temperature hinggalah ke 100, 200, 300, depends on materials. Kalau steel tu setakat 100, 200 dia tak ada apa-apa impact pun. So that's the reason you nampak dia macam flat kat sini. Okay, sebab dia masih lagi tak mencapai 1/3 daripada melting point pun setakat 100, 200 degree Celsius. So you increase temperature macam mana pun impact load dia sama saja. Okay, tapi at one point, they are very half of this transition behavior. You may see that dekat tengah tu, okay, is a point where transition will occur. Okay, this temperature indicate perubahan yang sangat large absorb energy, large impact resistant behavior. Okay, this value indicates the temperature for the ductile to brittle transition. So if you want to design the materials, where is the what kind of curve that you want to obtain? Is it this behavior will become shifted to the left or to the right, or what? What do you think? Apa dia? Tak dengar. Apa dia?
To the left. To the left, madam.
To the left. Okay, that's possible, meaning that we don't see this transition at if we slightly reduce temperature, because the transition will occur at very far lower temperature. So it's safe if we reduce a bit of temperature. Another thing, we want to design material that doesn't show this at all. Or if there is a change in the absorbed energy behavior at low temperature, maybe it just reduce a bit only. Okay. For example, okay, maybe we can design something that reduce a bit only. Okay. Or kalau pun macam ni, maybe something like this. Okay. Shifted to the left, or the changes in terms of the absorbed energy over the reduction of temperature is not really significant. If possible, flat like this. Okay, mean it doesn't show the transition from ductile to brittle when we decrease the temperature. Okay, so when you select materials, it's when you know that your structure will experience this kind of phenomena. For example, you nak create shutter space punya structure. Dekat bumi ni dia akan passing through normal temperature, room temperature, it passing through the level of ozone, maybe the temperature will increase, and then suddenly at the vacuum temperature will be lower. So there are a range of temperature changes, a large range. So you need to consider this kind of design. So it doesn't show the transition behavior from ductile to brittle. Okay. So this is brittle fracture. Which is why it is very dangerous, because it doesn't show any warning. Okay, that's the reason when we study about the failure behavior, we always want to consider the ductile failure behavior. Okay, when we do the testing, we look at the behavior during the fracture, whether it is ductile or brittle. If brittle, we need to be very careful. Okay. Because there's no warning. Kalau ductile, if you see it is bent, okay, there is some region, some allowable plastic deformation, you know, oh, something wrong with it, okay? But for brittle, it doesn't show very much plastic deformation, okay? For example, this one, okay, for this shape fracture, of course, one is a very flat surface. Another one, there's no reduction in the thickness for the shape. Kalau dimension berubah, if the dimension is changed, meaning that there are thinning of the vessel thickness, okay, due to the corrosion or whatsoever, maybe it doesn't support the initial design of the load. Okay, kalau structure tu dah berkarat, so maknanya dimension dia dah berubah lah. Thickness structure tersebut berubah. So sepatutnya yang tebal dia boleh support load 1000 ton. But if the dimension is reduced, the thickness is reduced, mean it doesn't support the same load anymore. Okay, so that's the reason brittle fracture, you don't see a reduction in the thickness of the shape. So it is brittle fracture. Okay. So another failure, we call it fatigue failure. Fatigue. You know what is fatigue? Fatigue is lesu, penat. Okay, tired of the material, tiredness of the materials. Why? Yeah, if you are given the same assignment, do it the same all over again, you same routine every day, you will become tired. Okay, same goes to the structure. When you give a repetitive load, cyclic load, on and off, okay, so the material will fail due to this phenomena. Okay, most fatigue failure are caused by cyclic loads. Okay, significantly lower than the load that should resulting in yielding. For example, the steel has a yield strength of 200 megapascal. But if you give a load lower than that, for example, 100 megapascal, but the cyclic frequency is very high. Okay, number of cycles is very high. So one day it will fail, even though it doesn't even reach the yield stress. Okay, sangat really dekat lah safety factor 2. Factor of safety 2. Okay, meaning that dia takkan fail lah kan. But actually it may fail. So that's the reason you need to consider about the fatigue failure. If it's involved cyclic load. Kalau static load, no issue at all. But cyclic load, contohnya macam contohlah Yang cyclic load yang ada benda yang boleh measure. For example, a timing belt. Okay, your service for the car. Kan engine tu kan bergerak berputar-putar-putar-putar, isn't it? Cyclic load. So there is a limit. After 100,000 kilometer, there is some service. After 10 kilometers, the kilometers indicate the cycle. Okay, they know after this cycle, the material will fail. Even though the design is safe. If they can, kereta tu boleh laju sampai 200 km per hour, speed dia, they have designed it, but there is a limit. Kalau dia selamat untuk that particular speed and load, kenapa kita kena tukar some part? Kenapa suspension kena tukar after this part? What's happened? It is actually because of the cyclic load. Okay, even though it can support the load at that limit, you put the safety factor, which is half from the actual load that give the plastic deformation, but still there is another failure may occur, which is a fatigue. Okay, so let's say for example like this, you give a load, okay, like a suspension of bridge, your car suspension, okay. So this, even though the load is lower, very much lower, but still can cause a failure. We call it fatigue failure. So the stage during the fatigue failure, okay. First it will show a crack nucleation, and then sorry lah, I forgot lah dia punya part CX and Y ni. Time versus nantilah I betulkan. So the behavior, the first is crack nucleation, okay, and then it increase crack formation at a steady behavior, crack growth there, okay, steady behavior, and then fast fracture. And if you look at the surface of fractured sample, you can see a dark area like this, okay. There is a line, several lines form at this region, okay. The first crack initiation is at this point, okay. The second region, second state, okay, the stage number 2, steady state, is this region that where you can observe a lines formation here, and then this one is very bright. Why bright? Bright because it's experienced brittle fracture. Okay, brittle fracture. Okay, this is indicates if you find any fracture sample like this, where you can see an obvious line, a beach line like this, dia ada macam bentuk kesan ombak dekat pantai tu. Okay, a beach line like this. So it means the metal failed because of the fatigue. Okay, and the half of this region, the bright region, shows the brittle fracture. Okay, if you look at this, of course you can immediately identify this is because of the fatigue. Okay. Okay, for example, the structure like this, okay, of the window, there are the formation of crack start at this corner. Okay, so this can be initiate the crack, and you know that the vibration of the huge structure like this, small vibration can influence a very high cyclic load for that particular structure. So for the fatigue test, okay, so why we do the fatigue test? Because we want to know what is the maximum cyclic number of the load that can be resist for the structure. Okay. So for example, this is by using the tensor test, we give on and off load. You pull and you release the load, pull and you release the load. So maximum loads that you give, and for this part is this is initial mean free with the load. This is tensile and this is compression load. Give on and off, tensile and compression, tensile and compression. Okay. So and then after several cycle of number, it will fail. Okay, so and then we plot like this. Okay, the stress we apply at okay. Okay, like this. This is the stress we apply for this one. Okay, let's say stress number 1, and we look at what is the maximum limits cycle load, the number of cycle load, and then we plot like this. Okay, for example, this one is 320, and it will fail. Okay, tak ada cycle number kosong, fail. 300, it will fail after 10 cycle of load. 250, it is about 100 cycle. What about if we apply 200 megapascal load, maximum 1000, and then 150, 10,000, until we get a flat curve. Okay, so flat curve, we call it endurance limits. Endurance limit, meaning that unlimited cycle number, very low load. So that will be safe forever. Okay, so this is fatigue limits. So if you apply this load lower than this one, it will be safe. Okay. So creep, another one. Okay, sorry. Okay, 2 minutes. Creep is a time-dependent deformation under a certain constant applied load. Generally occur at a high temperature. Okay, when we talk about creep, there is a temperature induced. Okay, we call it elevated temperature. High temperature is not lower temperature, where if lower temperature, it will shows the ductile brittle transition. But this one is failure because of high temperature. Okay, constant applied load. There is no cyclic. Okay, constant load generally occur at high temperature, but it can also happen at room temperature. Why? Because that temperature sufficient enough for the changes in the microstructure. Okay, for example, lead timah. We use lead, not timah. Timah is tin. Lead and tin. Okay, we use for soldering materials. Okay, dalam electronic component, inside the electronic component, there are so many soldering materials. You join between the transistor and the motherboard. There is some electronic component. You need to make it conductivity. You connect with one component with another component by using the tin and lead. Or sometimes now, I think now they don't use lead anymore, but tin. Okay, tin, gold, and everything. The melting temperature is quite low. So if you reach only 1/3, 1/3 from the melting temperature, you may induce creep behavior. Okay, 1/3. Kalau timah, if tin, standard tin, the melting temperature is around 230, 250. 1/3, not 1/3 in degrees Celsius. 1/3 of the melting temperature in the Kelvin. So you can calculate lah 1/3 of the melting temperature for the tin at Kelvin degree Celsius. Then you convert back at the degree Celsius. You may obtain it is about 20 or 30 degrees Celsius at room temperature. Room temperature, it may induce the creep behavior. So always remember this. There are some another failure, not because of the fatigue, not because of the fracture, but it because of the creep. Okay. You only apply a constant load. Okay, but it takes very long. There is some time influence in the in this failure. Okay, why? Because it may soften. Okay, soften, so the punya tensile strength is not similar anymore. The yield strength is not similar anymore. It may affect their strength. Okay, elevated temperature can cause material to lose their elastic limit under prolonged stress. Okay, because why elastic limit? Because the yield strength is reduced. Okay, the materials lengthen irreversible over a longer period of time, no matter how low the tension is applied. Okay, this is the mechanism of the creep, right? Okay, the slip will, the vacancy will produce at high temperature because the atomic bonding is weakened, and when there is more vacancy, the slip will climb effortlessly. Okay, primary creep behavior, it increase slowly, and then constant and very sharp increase in the strain over the time. Okay, secondary creep, uniform rate, tertiary, accelerated, and terminates immediately. Okay, this creep failure is one of the most important failure modes for the turbine blades. Okay, sealing collapse because the material softened. Okay, maybe the joint, one part of the joining materials they use for welding or whatsoever fails. Okay, and in summary, fracture may occur by ductile and brittle modes, where both involve the formation and propagation of the crack. Possible for material to experience ductile to brittle transition. Okay, fatigue, we have also, other than fatigue, we have also creep failure behavior. I think that's all for this chapter. Do you have, and if you have any question, I think tomorrow we can share. You can share your question during the class, and see you tomorrow.